why it's called process 1. And this process starts off again as executing all the only the parts of the kernel, but it builds a normal context and then switches to run as a normal user process, running a program which is called init, or a program which might be substituted for this init program. And this init program, the original one, which is still used in a lot of distribution, is configured using the init tab. And on the basis of this init tab, the parameters included there, the init process builds all the hierarchy of user processes until login shells, which then allow users to log in and build lower levels in the hierarchy, that is user processes created by the login users. Okay, each process can terminate using exit function, and each process must terminate using the exit function. There is no alternative. However simplified is the operating system. Even embedded systems, they use the exit functions. They might not have multiprocessing, they might not have any other features, but they still use the exit function to exit code. So that's also an important function. The exit function is if you write a program or a script, when you reach the end of file, end of program, then the exit code is invoked anyway. So even if you don't write it explicitly in your program, it will be invoked. The exit function has an exit code. That means by means of which you can signal if the program has terminated correctly or if there were errors and it had to terminate due to errors. Okay, the normal convention, it's not a requirement, but it's a convention, is that a properly exiting program exits with the value 0, whereas if a program terminates due to errors, it should exit with a value which is other than 0. That was the Unix convention. In later development of Unixes and from the beginning in Linux, this convention was even more strengthened, and the new convention is that 0 code means proper termination, negative values, because exit code is an int, so it might be smaller than 0. If the exit values are, they represent error codes. That means if a program terminates with negative value, it signals that that there was an error during its execution. And if you use positive numbers, then it's not normal termination, but it's not an error. That means if you want to distinguish different exit points, you might use positive values to distinguish between them. But as I have said, all of this is a convention. It's not a strict requirement. That means if a programmer doesn't follow the convention, then something different might happen. And then you need to read the documentation of the program to understand the different exit codes being used. Okay, so the exit code is produced in a process which terminates. When the process terminates, everything disappears. So there is no normal method of passing the exit code. This has to be handled by the operating system kernel, and as I have said, it is handled in the sense that every terminating process, when it terminates, it remembers the exit code in the process table, in the record connected with that process in the process table. So it's an important part of Linux program development, program running, to ensure that such processes which have already terminated but which cannot be removed from the process table because they store the exit code, that they are removed as soon as possible. To do that, you usually call from the parent the wait function. The wait function suspends the program and the process sleeps until a child is terminated. If a child terminates earlier, then the wait function does not suspend the program, and the process is immediately going on with the processing. During the wait function actually reads the exit code from the process table. Of course, that's an operating system function. That's why it can do it. Your program couldn't access those values because it can't access kernel memory. But when it received, when this value is read by the parent process, then the process is erased from the process table and the slot is freed to be used by a different process. Okay, so that's the purpose of using waiting. Important thing is that you don't really, you shouldn't wait for a specific child process. If there is more than one child process to the parent process, then the wait will be exiting on the first one, which stops. But of course, since the parent process knows what is the process ID of the child, it can then programmatically, you can write the code that it waits for a specific child process. Okay. If the parent terminates before the child, okay, the child would become orphaned. Such a child, we need to do something with that, because even if the child process terminates, it will not free the process table slot, because it will still require some parent process to read it. Okay, so we need always a parent, and for that reason, in Linux, in Unix, all orphaned processes become children of the init process. And inside init, we can define, using the init tab notation, what happens then. What happens when the process terminates? Whether it should be just the wait should be performed and removed, and that's all, or if the init process should respawn some other process because of the termination of the child. So you have then a choice of configuration when you're configuring the operating system. Nowadays, usually it's already configured when you get a distribution. It's almost nobody changes the init tab, and everything is running because it's already prepared. Okay. An interesting thing is that sometimes you need to run a program as a function. That means you want to, when you are running a program, you don't want to create parallel processing. Instead, you just want to run another program, capture its results, and then reuse them in your program in some way. To do that, you have a problem, because as I have said, to run a program, you need to use fork, okay? But then you are running two parallel programs. So in the parent program, you need to suspend the program, call wait, and in the child program, run the program, load the program, and run the corresponding process. When the program ends with some status code, the wait is the parent process is awoken from the wait function, and then the status is in the status you get the process ID, not the process ID. The result of the return value of wait is the process ID of the child process which is doing it, and in the status argument you get the return code of that process. So that in that way you can run a program not in parallel, but wait with the parent until the child ends. Okay, so I have here shown some other system function, which is not actually a process control function. It's a function which is for loading the program. The function exec is doing that. In C, there is not a single exec function. Also in the Linux operating system, there is more than one system function which is used for loading a program. They are all called exec, but they have some distinguishing letters. So there is no exec as such a system function, but there is exec with one or two letters added at the end. Depending on the letters, there are different, the exec prepares the program slightly differently before loading, and the loading process is slightly different, but that's not really interesting unless you need to use it. What I would like to pass on is something which some of you have already been doing last week during the laboratory, that is to speak about threads. Okay, what is a process? A process is a running sequential program which has resources associated with it. So basing on running programs, on processes, you can build a multi-process program. That means you can create multiple processes, and each process will have its own memory space. It will have its own copy of the memory. So there will be no simple communication between those processes. Of course, there are mechanisms for communicating between processes, but mainly processes were developed to maintain strong separation between the executing of the different tasks. That's necessary if you allow multiple users to operate concurrently in the program. It's also necessary if you want to run in different windows, different programs concurrently. Okay, so because of that, it's very important to have a very strong separation between the memories of the different processes, between the other resources allocated to processes. Actually, it's not so important to have just to have parallel processing. So a way of achieving parallel processing is to use the fork function and to have multiple processes, but it will not be very efficient. To improve this efficiency, the programmers, not programmers, but software developers have thought of a different mechanism, a mechanism based on threads. That means we have a single process, and inside that process, we have multiple executing threads. Okay, so what is the main difference between the thread and the process? Actually, there is one significant difference. Because in case of processes, we have two things in the same mechanism. Sorry? Okay, sorry. Maybe I am just too far from the microphone. Okay, sorry about that. So if you have problems in future, just tell me, because I might forget about this. Okay, so if we have multiple processes, we have multiple collections of resources allocated to each, and we have parallel processing. We switch the processor between the processes. So the idea with the execution threads is to switch processing without switching resources. So a thread is a process without resources of its own. So if process is connected in this case with resources allocation, and threads are connected with execution. We switch between executing threads, the processor, but they share within a single multi-thread process, they share the same resources, the same memory, the same open files and things like that. Okay, so in case of threads, of course, each thread is always sequential. In case of processes, if the processes are single-threaded, they are sequential. If they are multiple-threaded, they are not sequential. So what do you use threads for? You use them to parallelize your code, also to simplify asynchronous events handling. Okay, you can do it by hand, so to say. If you have multiple asynchronous events happening, you can each occurrence of an event queue in a queue and have have your program execute event after event. This is called event programming, and it's quite popular nowadays. But the problem with that is that all the synchronization between the events, the ordering of events has to be done in a single program. Another approach, which is in a lot of situations much simpler, is to handle different events by different threads. So a thread might be might be suspended, waiting for an event to occur. When it occurs, it handles that event, but at the same time, other events are waiting on other asynchronous events, and that way you can have a simpler program than queuing the events and having to maintain by hand the sequences and the interaction between events. So this is one of the techniques of programming which allows you to handle asynchronous events quite efficiently. And also nowadays, it's also important that if you have a multiprocessor system, if you have multiple threads, they might be executed really in parallel. So in those situations, you can also achieve faster processing. But if you have a single processor for multiple threads, then you don't get any benefit of speed up of your process, of your program. So the speed up of programs is not the main goal of using multi-threading. It's actually asynchronous events handling, which is the most important why we use multiple threads. Okay. There are two separate types of thread implementations. Okay? One approach is to write a program with a scheduler inside the program. So we have an operating system scheduler which schedules the processes, and inside the process you have some part of the code linked in the program, which switches between the multiple threads, which we organize purely programmatically. In such situations, the operating system doesn't even know that you are using multi-threading, and it is allowed, this approach it used to be very popular. Now it's less popular, but it's also possible. Another approach to thread implementations is to have the threads implemented by the operating system. That means in such situations, threads are actually similar to processes, except that they share between them. If they are from the same process, they share all the resources, especially memory. This approach is implemented in Linux, and if you are working with pthreads in the laboratory, by default you are working on system space threads. Okay, in fact, you can use pthreads to be working on user space threads, because pthreads also supports that, but I don't see any point in that, and at least at the moment nobody is doing it in Linux systems. Actually, this distinction between system space and user space threads is actually even more complex, because you can map between user space and system space threads. Okay, user space threads are those that you see when you are programming, whereas system space threads are those that operating system sees. So in Linux, by default, the mapping is 1-to-1. One user space thread is one system space trace, but you can also have mappings multiple user space threads to a single system space thread. And that used to be the case in older software. Nowadays, it's not really used. Both Windows and Linux use them one-to-one mapping. Okay, so that's the execution thread, and of course the execution threads, as I have said, they are actually a programming concept, and as such, they are supported by different libraries. One, probably the most popular at the moment, is the POSIX threads library. The P in threads stands for POSIX threads. That's what we are doing during the lab, what I described in the instructions. Starting from C++ of 2011 standard, threads became a part of the language, not of the libraries or APIs, where you can choose between different, but threads became a standard in C++. So the newer C++ compilers, or in case of JCC or J++, you need to use the option which tells them to what standard of C++ you are using. So if you are using them, you can compile, you can use pthreads directly from the language. It is packed in some classes. The thread class is the most important, but actually, when you look at the linked program, it still uses pthreads, only you are using C++ language to package it more conveniently for C++. And there are a lot of reasons to use this instead of the POSIX pthreads directly. But of course, you need to understand the pthreads, and so I have decided to concentrate on pthreads during the lab. In case of Windows, of course, Microsoft never uses standards made by others, so they have their own standards for multi-thread programming. This is called Win32 threads, which are very similar to pthreads, but they have distinctions. Okay, a bit different is, but you can also be using. You already studied using threads in Java. Of course, in case of Java, Java is not compiled to binary machine code. And that means that you cannot really use directly threads, the POSIX pthreads, because you can't use a library, a C library directly. So instead, Java has developed their own definition of packages, of threads packages, which are executed by the virtual machine, but not by the machine code. Of course, the virtual machine is multi-threaded by itself, so it uses POSIX threads, but because it's written in C, not in Java, but everything above that, that means everything you program in Java, if it wants to use parallel threads, it uses Java threads. Okay, and then we have connected with each library, you have the programming APIs, that means the sets of different functions that you can invoke. You have already tried creating, joining, and canceling threads. So all of them are supported by the different libraries. The APIs also define synchronization mechanisms, about which specifically I will be speaking next week, but in general, how to approach it, I will be speaking of today in the second part of my lecture. A very important thing about multi-thread programming or parallel programming in all is to understand the concept of reentrant code. Okay, you might have more than one thread running in parallel or concurrently. I have said there is a difference. Fully in parallel is if it is running on different processors, whereas when you switch between different threads using preemptive scheduling, we are talking not so much about parallel, but about concurrent programming. But it shouldn't be significant to the end user, because he shouldn't distinguish between the two. Okay, so if you have such a situation and two different threads call the same part of code, the same function, then you have a problem, right? Because the same code is being executed by more than one thread at the same time, okay? So this might be a problem, or it might not be a problem, depending on how your code was written. And so we say that a function is reentrant if it can be executed by two parallel threads at the same time without any side effects. That means the execution will be the same. If you think about it, when a thread or process reads the code to be executed, it just reads the instructions. It doesn't change those instructions. It knows what data to operate on and where to put in the results. So if the data is distinguishable and the results are put in different places, you have reentrant code. If the code is self-modifying, or if the code is putting data from different threads in the same place, then it's not reentrant, because depending on how this code is invoked by the two threads, it will cause indeterminate behaviors. Okay, so what happens really that speaking in C language, we require that the code is not self-modifying, which is usually enforced by the nowadays by the compilers, so you don't need to worry about that. But if you are programming in assembler language, then yes, you should remember about that. Then also the code should not have any static data. It should not be using static data. Static data is data which is stored at specific addresses. Okay, if something is stored at a specific address and this address is inside the function, then of course the code is not reentrant. If you pass on stack on some dynamically allocated memory, you pass to the function the memory on which it is operating, where it stores the result, then it's completely reentrant. Again, going back to C language, that means that you cannot use inside a reentrant function. You cannot use any static variables or global variables, but you can use locally defined variables because they are defined on the stack in C language. That means that if they are invoked by two different threads, each thread has its own stack, so will store the data on a different stack, and there is no problem. Okay. Some libraries, some functions, they also when you write your own functions, you actually should use a keyword defining something which is called here underscore reentrant. This is this define is mainly used by libraries, by static libraries when you are joining them to your program. It tells them to compile the code as if so that it is reentrant. So it's some information for the compiler, how to compile, and a number of different functions make use of this, that the different code is being created when you call define reentrant or when you don't. Of course, if you have a precompiled library, in that case, it's either compiled to be reentrant or not, and you don't have any influence on that. So when you are using curses, it's not reentrant, and no keyword, no define of reentrant will change that. But if you are writing your own code, or if you are using a static library, not which will be compiled by you, then yes, reentrant is important in such situations. Actually, if you compile with reentrant, usually the code is longer and is executing longer because it has to make certain that it is reentrant. So a lot of libraries are not reentrant to make them faster processing, assuming that nobody will be using them in parallel threads. Okay, so the next thing I would like to speak about is how you create a thread. Of course, pthread library has some functions. If you use C++ instead, you can use thread objects which are predefined in C++, starting from the new standard. But I will be speaking about pthread. You have a function which is called pthread create, which accepts as one of its arguments, it accepts the function which must be executed inside the thread. So when you call a thread create, you create a new thread, and as one of the arguments to it, you pass the function which is to be executed. There is no problem with C language with that, because in C all the functions are static and defined outside the scope of any other function. It might be a problem in C++. because in C++, a lot of the functions are not really functions, but they are methods. If you define a static function, that means you are not really writing in C++, but you are writing at that moment in C, and that's okay for the argument to pthread create. But if you want to use a method, a C++ method, then there is a pitfall which you will not experience if you, instead of using pthread create, you use this the thread object. But in case you use directly pthread create, the function being used in C in pthread create, which is passed as argument to pthread create, must have one argument, and this argument is a void pointer. If you use a non-static method in C++ method, then the underlying C function, which is connected with any method, has a hidden argument, the argument this of the, so inside non-static methods in C++, you can use this argument, and for that reason, the methods have hidden arguments to them, which you don't see, you don't define, but which are there, and they break the pthread create. But you can use a C++ static method, or you can use a C function as a stub function, that is a function inside which you invoke the C++ method. But you must pass to the pthread create a static function. Okay, if a thread is created, it immediately starts to execute. By immediately, I mean when the scheduler schedules it, because it becomes immediately ready, but executing when it gets the processor. Okay, and it will stay active until you either call pthread exit or you call a return from that function. So if you return from the function passed as argument to pthread create, it's exactly the same as if you called pthread exit. Okay. Actually, pthread exit accepts an argument, and also the function can, our function defined by us can have an int value return, and this return value is the exit code passed from the thread, similar to exit codes from processes. We can have thread exit code, but that's, well, I haven't yet seen a program which was making use of that, but you can do that. If you pass the exit codes, you can access the passed value by executing a pthread join. Usually you use pthread join for something else, something more than that, but you can also catch the value of the exit code. There is another way of terminating threads. It's by using the function pthread cancel, which is called from another thread. So maybe from the main thread, because when you start a program, it will start with a single thread executing the code of the process. Okay, and if you call pthread create, you create other threads. So from a different thread, you can cancel any other thread, also from the main program, because that's a similar thread to all the others. you can cancel any thread you want. Okay, when you receive a pet thread cancel, that thread terminates, but I will speak about that in a moment. Okay, and any function called by pet thread has one argument. In C, that means that you, and this argument has not, is defined as a void pointer, which means that it points to an undefined type of variable or structure or class, a class object, sorry, not class. In C++, this is simplified because you can use in Petret create methods instead of static functions. You can define any class objects directly, and Petret the function will understand different arguments, but in C that's not possible. Okay, so if it is a void pointer passed to the function, you can then cast it to any other structure that you know that should be passed to the to your implementation of the thread function. What is important is that the thread, the fact that you want to terminate a thread, for example, when you set a variable, doesn't mean that the thread immediately terminates. There is always a delay, and this delay can cause problems, because if you are executing the whole program, you are freeing resources. So the thread you are running, which if it delayed termination, might be trying to access memory or access other resources which have been already released in a different thread executing the exit function from the whole program. Okay, this is a problem, and I have dedicated a separate slide to discuss it so that you understand it better, because that is a problem really. Okay, so a thread delays its termination until normally it executes either a return or a thread exit. If if inside your program you have a sleep for 10 seconds and you change some variable so that the thread should terminate, it will test that variable until after it wakes up. So it might be after 10 seconds, for example, if sleep was for 10 seconds. Okay, so this is a problem with normal termination, that you signal that you don't want to kill in any way the executing thread, but you just want it to finish by executing a thread exit or return. Okay. So another technique is to send a pet thread cancel. A pet thread cancel has some advantages, but it also doesn't solve the problem really. Okay, because if you send a pet thread cancel, the compiled function being executed by the thread doesn't test for the cancel, if the cancel was sent or not. Similarly to your own program using a variable, it only tests at certain points. In your case, if you it tests when you are executing while variable or if variable. In case of pet thread cancel, it has a lot of defined cancellation points. all the pthread functions have as such cancellation points. So, but normally compiled code is not. Also, operating system functions or other library functions which are not pthread, not specifically developed for pthread usage, they do not have cancellation points. Actually, you can change the behavior of that by reprogramming, but I don't advise it because a lot of implementation, even even in Linux, will simply ignore it and use only deferred cancellation points. Okay, so because of that, you don't want to have inside your threads. If you want to terminate them from outside your program, from outside your thread, you don't want to have long periods without any cancellation points. In fact, the most significant from your point of view is the use of sleep. Okay, if you use the sleep function, it's very easy. Microsleep is just as easy, but it will not, it's not a cancellation point for pthreads cancel. If you want to speed up ending a program after some event, you use pthread cancel, and instead of using the normal sleep, you need to use pthread sleep, which is a function in the pthreads library, which is behaving similarly to microsleep, but it is a cancellation point. Okay. And the important thing, the most important thing is that since whatever you do, you have to count on threads to delay, you must be aware that if you execute exit, which is a normal exiting of a program, then exit will terminate all the processes, but it will terminate all the threads, but it will terminate them by sending pthread cancel. And it will not be waiting with pthreads join for the threads to join. Instead, it will just issue pthread cancel, and then it will start releasing memory, releasing other resources, because as you know, exit, you shouldn't, when you are programming, you shouldn't count on it, but in fact, exit does release all the resources, or should be releasing all the resources. So if that happens, your delayed termination process might cause you to access already released memory. Mainly it's memory, which is a problem, which would cause a core dump before ending the program. So instead of normal termination of the program, you get a termination with errors and with core dump. And core dump is done by the processes to allow debugging of why the process terminated abnormally, and it uses disk space, and it is generally a problem. So you use pthread join inside the thread, usually the main program thread, but it can be any. You use pthread join to wait for all the different threads to end, and only then call exit, call other functions which release resources, like Enduin also is such a program that's in the ncurses library you will be using in the laboratory. Okay, so that's all about processes, about threads. but not all about running programs in parallel, because we need to talk about synchronization, and that's the next part of my lecture. So I will stop for a moment sharing these slides and switch on to a different set of slides. Okay, so now you have the next set of slides from me. We will be starting the next topic, which is process synchronization. Process synchronization is aimed at solving problems with parallelly executing processes. Okay, and the main problem is that if you are doing some things in parallel, there might be some code which you don't want both the programs to, both the threads to execute at the same time. And this problem is called the critical section problem. So you have the code of one thread, you have a code of the other thread, and somewhere in the middle, you have something which we call a critical section. It might be an invocation of the same function in both the threads, and the function might not be reentrant or should not be called in parallel, so must be sequentialized or whatever. Okay, or it might be different code in one, different in the one other. The content of a critical section is completely separate from the identifier of the critical section. What we want is that the two critical sections with the same identifier are not accessed by at the same time by multiple threads. So what there are three requirements which are defined to solve the critical section problem. The first one is the mutual exclusion. Mutual exclusion means that at a certain time, at any time, not more than one thread can be in the critical section, or no more than one process can be in the critical section. Okay. So that's the only requirement, that for the time that the execution critical section is being executed, it is associated with one thread to the mutual exclusion of any other. Another point, another requirement is the progress requirement. If if no thread or no process is executing the critical section, you should not suspend it before entering the critical section. Okay, so the first requirement tells us that if a process is, or if a thread is inside the critical section, all the other threads trying to enter the critical section should be suspended. And now what I am saying is, if no thread is in the critical section, then all the any thread trying to enter the critical section should be allowed to enter. So the first that tries to enter the critical section should be allowed to do that. And there is a third requirement, which is very difficult to illustrate in case of two processes or two threads, is the bounded waiting. That means if a thread is suspending, waiting to enter the critical section, there is always a danger that there will always be a different thread also trying to enter the critical section, and this one very unfortunate thread will never enter the critical section. Bounded waiting means that every thread will enter the critical section sometime if it needs to enter it. Okay, that it will not be infinitely being suspended. So the bounded waiting in case of two processes or two threads is actually very difficult to achieve unless you write your program in such a way that one thread is all the time inside the critical section and the other is waiting for to get into the critical section. So if every thread leaves the critical section in reasonable time, then in case of two threads, there is no problem. You don't need to consider the bounded waiting problem. So in case of two threads, bounding waiting is exactly the same as starving of occurring between threads. In case of multiple threads, even if there are no starving, it can still be a problem. But usually bounded waiting is connected with starving of processes. Okay, I will be speaking just processes, not saying process or thread, because in this case, it's something which doesn't matter. It will only depend on what mechanisms are available to solve the problem, not on the problem by itself. Okay, so let's consider a few solutions, a few possible solutions. The first solution, it's very simple. You just, and it's purely programmatical. The whole point is that you can solve critical section problems completely programmatically, but it's very difficult in some cases, depending on the number of processes. In case of two processes, there is a published solution. In case of three processes, there is also a quite commonly known from books solution. In case of four, if you study the literature, you will find a solution because it's an old solution because nobody is using it nowadays. But if you are very determined, you will find it. In case of five, I don't think anybody developed a solution, and you will see why in a moment. Okay, in case of two processes, you can use just a single variable at the beginning of a critical section and test the state of that variable. Okay, since the same variable at the same time cannot have two different values, so in this case, you will be, if the first process reaches the critical section, it will have, next will be in value 1. So while will just pass through, okay, we'll go into the critical section, and we must prevent the second process from entering the critical section, okay? So if the second process reaches the critical section and we haven't yet exited the critical section, next will be 1. So this process will loop inside this while loop and will not enter the critical section. Okay? When process 1 leaves critical section, it sets the value next to 2, and at that time, process 2 can enter the critical section because this while loop will be solved. Okay, the problem with this solution is that it does not it solves mutual exclusion, but it does not solve the problem of progress, because if process 1 leaves the critical sections and after some times reaches again the critical section, and in the meantime process 2 has not reached the critical section yet at all, then process 1 will next will be have value 2, so it will loop in this loop instead of getting into the critical section, even though process 2 hasn't yet reached the critical section. So actually, this solution sequences the entrances to the critical sections. That the entrances must be interleaved. Process 1 enters, process 2 enters, process 1 enters, process 2. That's not correct from the point of view of the progress requirement. Okay, so let's see another solution. Okay, so another solution is to use two variables, two flags really, because those variables can need only to assume two values. Okay, there is one variable, one flag for entering critical section 2 and one for entering critical section 1. Okay, so at the beginning both are zeros, so whichever process reaches the critical section as first, it will set the flag either one or the other to 1. Then it will loop. It will not loop because the other is not in the critical section. So it will enter the critical section. If the second process, the later to reach, reaches the critical section, it will set flag 2, of course, but it will loop on while F1, and only when process 1 leaves this critical section will it be able to enter it. Okay, it solves the problem of progress as such, but it poses a different problem. Okay, the problem is that our first program might reach the critical section, first process might reach the critical section, set the flag that it's entering the critical section, then it will start looping, but before it can test the value of F2, it will switch to the second process. Okay, the second process which will set flag 2, okay, will test whether F1 is set or not. It will be already set, so it will loop in here. But the first process has already tested that F2 is 0, because at the time while was being executed, F2 was being 0. Okay, it was set here to 1, but it's okay. No. Okay. Sorry. No, it hasn't yet finished the while. It just started testing and got switched here. So here, when it loops on F1, eventually it will switch again. And when it switches again, the the while loop will not be met because F2 has been set to 1. So it will start looping on this, switching here again, looping on this, and this is just blocked. Both the processes got blocked. So this is a possible situation where a deadlock occurs. Actually, this deadlock was caused by the fact that we have this order of setting the variable and testing the other variable. So we could change the order, but in that case, when switching occurs in between, you would find out that mutual exclusion would not be possible. Okay, so if we change the order, okay, we first test and then set, and we get to this point, then test F2 is not met, set F1, and then switch, or before setting to S1, switch to here. Okay, if it was before, then this while will not be, will also not suspend the program. So F2 will be set to 1, F1 will be set to 1, but they will not be tested. So both the processes will get into the critical section. So we haven't solved the problem of critical section at all. Okay, so the solution, there is a solution, as I have said. This is called Peterson's solution. It's one of two, actually, but it's simpler to explain than the other one, which solves for two processes the problem. And in this case, we use three variables. The next variable from first solution and the flux from the second solution. Okay, if you have here such a situation, okay, you might got switched somewhere in between. Doesn't matter. The second process gets here. Flag 1 was set. Next was maybe set, maybe not. But that doesn't really matter because next cannot have two values at the same time, and that's the only thing we are using in this solution. Okay, if the process is switched back, okay, either this process, so might happen that both F1 and F2 are set to 1, but next will be depending on when the switch occurs, the second switch. Next will be either equal to 1 or equal to 2, but never equal to both of them. So that means either this process or this will enter the critical section. Of course, this solution solves the critical section problem, but it is very wasteful with processor time because all the suspension is being done on a while loop. So the software solutions are not very good because they consume the processor time needlessly. As I have said, at a certain point, the mathematicians stopped looking for solutions to multiple process synchronization of the critical sections because a different approach, a completely different approach was proposed by Mr. Dijkstra, a professor from Holland, who has proposed to use some operating system support for this problem. And the support that was proposed by him, he called semaphores. That we have a special variable. It's an integer variable. That was his first proposal, because afterwards you've also modified it and proposed binary semaphores. But in the initial proposal, he proposed a counting variable, and that's why nowadays it's called counting semaphore, or simply semaphore, Dijkstra's semaphore. And such a semaphore had two operations defined on them. Those two operations were called from Dutch language V and P. I don't know what is the exact word, but it was these were the first letters of the words of standing for signal and wait in Dutch. Okay, and this notation V and P is commonly used, and you must understand it, because in a lot of documentation nobody will be telling you that the operation is signaling or waiting. They will just use the V and P notation. So the signal operation on a variable increase the value of the variable by 1. The wait operation or P operation on that same variable decreases the value of the variable, but it tests before decreasing if the variable is not 0, because if it is 0, the decreasing would cause the variable to become negative. Even though the variable is defined as an integer, actually a semaphore variable, counting variable, will never be negative unless there is a programming error, system function error, because that might be signaled by negative value. Okay, but if these two functions, how do they differ from the previous solution? The difference is very simple. This operation is done by the operating system, and the operating ensures that there is no switch between testing if the variable is 0 and decreasing the value. Okay? Instead, it will not be a fast loop like this, but because that would be a still a hot loop, which is not a good solution. But instead, in Dijkstra semaphores, in the operating system implementation, we test if the variable is non-zero. If it is non-zero, the variable is decreased, and there is no possibility of interrupting, of switching threads or processes while executing the P function. If the value is 0, the P function will put the thread to sleep. It will change the state of the thread to sleep, and the V operation implementation, when it increases the value of S, it will wake up all the sleeping threads or sleeping processes and make them ready. Okay, so in that case, there is no hot loop because the waiting process is put to sleep. Okay. In case of counting semaphores, in case of signal operation, the thread which invokes signal operation is never put to sleep, and the thread which but a thread which invokes wait operation can be put to sleep if decreasing the variable would cause the S to be the semaphore to become negative. Okay, so Dijkstra also defined a binary semaphore because he said, okay, for a lot of solutions, it's not needed to have multiple value S. So he defined an S variable, which, that means a binary, he defined a binary semaphore, which switches only between values of 0 and 1. Okay, definition of operation wait is exactly the same as in case of counting semaphores, but the definition of signal is that if semaphore is 1, it cannot increase the value to 2, and so it will also cause put the process to sleep on the V operation. So this is the difference between the two. In case of the simple solution, I will be ending on this my lecture because I have run out of time, I think. Or maybe still a few minutes. Okay, so as I have said, we are using putting processes to sleep and avoiding hot loop or busy wait. It's also called in those situations. In case of multiprocessor programs, when you write a program which has a huge number of parallel threads running in parallel and you use synchronization, then putting processes to sleep is might be time expensive in the time. In such situations, the busy loop sometimes is ignored, and there is a special type of implementation of semaphore, which are called spin locks, which are actually Dijkstra semaphores, but which really use the busy wait. That means they test in a loop. But normally you don't do that. And it's a big mistake, a synchronization mistake, to use busy wait inside parallel programming because it wastes the processor time. If you have a huge number of processors, you might not mind it. And in those cases, the wasted time of managing, putting multiple threads to sleep is more important than losing processor time. But in normal programming, normal situations, if you are not using the graphical card for multiprocessor programming, you don't use spin locks. You use semaphores. Or if you have a semaphore, there is a very simple solution of the critical section problem. Solution which works not only with two processes like Peterson's solutions, or with only 3 processes, but it can be used for any number of processes. You use a semaphore, set it initially to value 1. When entering a critical section, you call the wait operation. When leaving the critical section, you call the signal section. okay? And you may see that this solves the problem. The problem is actually solved by the fact that you cannot switch between the two inside the P and P functions. Okay, so we have run out of time now. Thank you for your attention. I will stop sharing the screen now. If you have any questions, please let me know. No, I don't hear anybody having problems. So I hope that you have understood it. These are quite difficult topics that I'm now covering. So if you have any doubts, please ask them. So in 10 minutes, I'm meeting with some of you for the laboratory. So I need to end now the lecture. Thank you very much. Bye.